Hey everyone, I'm Teresa. I'm a solution architect manager at NVIDIA, and I work with robots most of my time. So I'm here to talk a little bit about physical AI and how we're seeing the evolution of AI in general, but also give some context on how you can start building and what are the key workflows that we have in terms of actually building physical AI models. And I want to start with some context on the evolution of AI. And so neural networks are not necessarily something new to us, but we first had the big boom of deep learning into around 2012 with the invention of AlexNet. And then we started seeing a lot of interesting applications, particularly in terms of perception AI, speech recognition. So basically we started having AIs that can do some sort of identification of images, text, or speech. After that, we started basically seeing a big boom of things like language models. So instead of just understanding information, we also generate information. And I would say right now we're pretty much in the world of agentic AI, where people and enterprises are starting to use AI systems to do some sort of tasks in the digital world. So things like coding assistants, customer service, and so on. Now the next phase and the next wave is how do we bring these AIs into the actual physical world? So in this case, we embodied this a lot in the context of autonomous vehicles and also general robotics. And so the idea here is how can we actually make and build AIs that can understand but also act in the physical world. And so again, the context of intelligence machines are also not very new, so we've had robots for a long time. If you look into the main industries, there are a lot of robots out there actually. The problem is a lot of these robots are pretty dumb, so they're not very autonomous. They're very pre-programmed, so you can do a lot of different things, but they're only good at doing those specific things. So the moment you change something in the environment or in the process, they start to fail. And so the new kind of shift in terms of robotics, but also physical AI, is building more foundation models. So how do we take things like sensor raw information, and then how do we generate actions? So instead of the typical LLM type of models where you generate text, here our tokens are basically actions in the physical world. Now, physical AI is actually pretty hard to develop. So the biggest problem, one of the biggest problems, is that real-world data is really costly to capture. So generally you need very expensive hardware, it's very time-consuming, and it's generally something that it's pretty hard to do. And then the second thing is obviously actually testing these robots is actually pretty expensive and can be dangerous. Not all robots look as scary as these ones, but it's still pretty expensive to test these. So generally robots are pretty expensive in terms of the hardware, and so it's kind of very time-consuming. But also in a lot of cases, you want to build AIs and robots and autonomous cars that can handle a lot of different potentially dangerous situations where you don't really want to actually get this sort of data and test it in the real world. And so we call this a little bit the big data gap in robotics. And so going back to my evolution of AI, one of the big things that really helped us kind of with this boom of generative AI is the fact that we have trillions of tokens available on the internet to train these models. Same with agentic AI, we started having a lot of reinforcement learning techniques with a lot of largely data sets. And so the key here was you have a lot of data, you throw a lot of data into a lot of compute, and you have a lot of interesting and very impressive models. And so the problem with robotics is that we don't have that data. And so the key challenge here becomes how do we turn a typical data-bound problem into a compute problem in a way. So that's kind of what we're trying to solve a little bit. And to give you a little bit of context on the types of data that we're talking about, I would say this is kind of the data pyramid for robotics. So at the bottom you have basically a lot of data, generally in the web, but this data is very unstructured, generally pretty low quality. But you can train a lot of these models, for instance, in terms of vision and language understanding, you can take a lot of this information already. At the top level, you have something like real-world data, which is very high quality in general, but also very small, very time-consuming to capture, and also pretty expensive, and generally lacks a little bit diversity as well. So you can have a robot capturing some data, but then it's basically really hard to get a lot of diversity in that data. And so at the middle layer, and this is the layer that we're trying to focus a lot, you can have synthetic data. And so this is a little bit lower quality than real data, but in
principle, it can actually be really easy to scale. And so that's one of the key things that we're focusing on, is how do we grow this middle layer in order to build better models. And so the two key platforms that we're focusing a lot at NVIDIA on, one is our NVIDIA Omniverse platform. So this is basically a simulation platform. We're using that for digital twins, but particularly for training and testing robots. And so we generally say and believe that every robot will learn how to be a robot in simulation. And then the second one is something a little bit more recent. So it's the concept of World Foundation models. So in case you're not familiar, these are basically neural networks that understand the physical and the spatial properties of physical worlds. And so with that, we recently released a platform called NVIDIA Cosmos, which I'll explain a little bit, so it's a little bit more recent. But both of these are very interesting for us to basically generate a lot of this data that we need for robotics. And so the World Foundation models, you can have different types of World Foundation models. For us, and I'll talk a little bit about these three. So the Cosmos Predict model is basically a diffusion model that can predict the next actions, and the next video and also actions. And so the idea here is you give, for instance, a few seconds of a car or a video of a car, and then you prompt the model with, okay, now the car is turning left. And so the video that gets generated is basically a pretty consistent video of a car turning left. So this can be really interesting in terms of generating a lot of data that we need to train models. The second model is Cosmos Transfer. So in this case, we're maintaining the structure of the video that we're generating, but it can change a lot some parts of the video. So for instance, if you want to change the background, but keep the robot, or if you want to change the texture and the materials of a table, you can do a lot of these pretty easily. And so this is very useful for things like visual augmentation. The last type of model is a pretty different model, is a reasoning model. In the context of robotics, this can be very interesting for different applications. Particularly for the thinking and planning of the robot brain, where we're using a lot of reasoning models as well. So it's a little bit some of the introduction. Now I want to talk a little bit what it takes to build some of these physical AI models and what are some of the key workflows. So the first one is, as I mentioned, the creation of large and diverse data sets. And so this is generally the first step. I'll show some of the examples of some of the workflows. This is a workflow that we have for motion generation, for manipulation. And so here, we basically start with some sort of teleoperation. And this is a teleoperation in simulation, so the robot in simulation, but a human is basically doing the task of the robot. And so with this, you can capture a few demonstrations, like say tens of demonstrations. Now, also still in simulation, we use an algorithm to basically do trajectory augmentation. And so here you're creating different variants of that specific motion to create already maybe hundreds of motions. And so you already have some sort of augmentation. And then at the end, we tie this to the Cosmos Transfer model. And then the idea here is to really go to thousands or even millions of training data by basically creating a lot of the visual augmentation, changing a lot of the context, the scene, the lighting conditions. This was particularly interesting and very important because generally the perception of the robots is very sensitive to anything like lighting and textures and things like that. This is an example with the autonomous robotics ultrasound model as well. So what you see here is the type of augmentations that we created. So at the top you have the simulation and the ground truth. We also use some ground truth information like depth and segmentation, such that you can control what you want to change in the video. And then we're creating several variations with different types of tables and background and lighting. And these are some of the results that we got in terms of, we saw maybe around 80 to 30% improvement of the base policies of the robots by adding this sort of data as well. The second type of workflows that we also use a lot is with the Cosmos Predict model in this case. And so this is a little bit of a different workflow. We're not using a classical simulation here, but we're inputting some sort of initial frame. Let's say in this case we have an egocentric camera of a robot with an apple. And then basically we're generating a lot of data with Cosmos Predict model with different environments and slightly different conditions as well. We also, it's kind of a multi-step problem and solution in this case, because the Cosmos models generally can generate the video, but to train robot policy, you also need the actions. So once we have generated that amount of video, we basically also extract the actions with action labeling. And then at the end, you can have a very large data set to train some sort of robot policy. Okay, so now we have the data, so we need to train a policy, and we also need to test the policy. So I'll talk about these in conjunction, mostly because they use a lot of the same platforms, but also because the idea is that you can have very fast iteration loops on your policy if you test it in simulation first as well. And so to give some context on the type of robot learning and AI models that we use in robotics, the first few ones, I think everyone is probably very familiar, so supervised learning and unsupervised learning. The two ones that a lot of people are using these days for the physical AI applications are reinforcement learning and imitation learning. So with reinforcement learning, you're basically learning by trial and error to maximize some sort of reward. So generally this is really interesting, for instance, to train the control of the robot, or to train a robot on how to walk. So anything that you might need to learn from scratch. And then imitation learning, you're basically learning by some sort of mimicking some demonstrations, for example, from humans or from other robot data. So with reinforcement learning, the key thing, again, is to use some sort of simulation environment. For instance, this is an example of a robot learning how to walk. Now, obviously, in the real world, babies might take 1 or sometimes 2 years to learn how to walk, and we cannot afford to wait for 1 or 2 years for a robot to learn how to walk. So the idea is that you can do this much faster in simulation because you can parallelize a lot of the exploration that you need to do with reinforcement learning. So here we're using Isoclub application on top of Omniverse to basically do that parallelism, and then also for robots to basically learn how to walk. And so we are using this sort of simulation platform. It's a pretty high fidelity in terms of physics simulation. It also simulates, based on our RTX technology, so it also simulates light. And this, as I mentioned, is actually pretty important because, for instance, if you change this to a transparent floor, obviously that impacts the lighting simulation and the perception of the robot, so you want to simulate that pretty accurately. And then once you test that, and once you train the model in what we call Isoclub, then we test the model at scale with software in the loop, testing with our ISC application. And these are just some examples, again, on some sim-to-real transfers, which were also pretty good in terms of being a zero-shot transfer to the real world. So this is the same autonomous ultrasound robot. Here we have a manipulator doing a gear assembly and manufacturing task, and there we're basically teaching a robot dog on how to walk. The second key concept that I mentioned is basically learning by demonstrations. So here, a lot of the new types of models that people are building are called vision language action models. And so here, this type of models basically take some sort of input, which is basically some image observation. It could be from a camera of a robot, or even an outside camera. You take in the robot state and answer some sort of language prompt, and then the output are basically actions for the robot to take. So here we are building ourselves one of the robotics foundation models called Root. There's also a lot of other interesting models out there. For instance, Google has Gemini Robotics. There's also Bizio, which is another very interesting model. A lot of these models are kind of converging to this system 2, system 1 type of architecture. The idea here is that it follows a little bit the way that the human brains also work. So we have this very thinking, reasoning part of our brain, but a little bit slower. So that's the system 2, which generally is a visual language model. And then we have a more fast, intuitive, like control, reactive part of our brains. That's the system 1 in this case, which in this case is the diffusion transformer model. And this is just an example of one of the demos that we did recently. It's actually a pretty cool demo because a lot of the early VLA models are pretty good at short horizon tasks, but not really long. So in this case, we're actually combining a little bit some of the technology that I mentioned earlier. So we have a good model, but the way that the robot is moving is actually trained with reinforcement learning. And then here, we also have the reasoning capabilities of the new root model. And so the person is basically asking the robot, hey, can you bring me the healthiest snack? So the robot is basically navigating to the specific spot, and then is looking at what is available and defining what's the healthy snack. So let's see if it actually can find a healthy snack. And this is where things like reasoning models can be very interesting, because it also makes the robot to think about what it's seeing. And so in this case, it's kind of properly finding and thinking that the apple is a little bit healthier than the chips. Then I won't show it until the end, but basically it goes back to the person and then it gives the person the apple. Okay, and the last part is obviously you train a model, you generate data, train a model, test and simulation, have this kind of flywheel, and then at the end you obviously need to deploy this also to physical robots. Here I won't go into a lot of details. I think the key thing is obviously we also, in our case, need to think particularly about these new types of models. They can also be quite compute intensive, so we have a lot of different things that you need to actually run on the robots. And so a lot of this is not very feasible for you to use things like data center GPUs. But it's pretty, like there's a lot of things here that need to happen on the robot. So things like reasoning, sensor processing, perception of planning, control, and so on. And so for this, we are using basically our embedded line. So this is one of our newest embedded GPUs. And it's a pretty powerful one that people are starting to use, way more powerful than earlier generations. And so the key here is to have something that is still very powerful, but also much more energy efficient to run on in each of the robots. And yeah, and lastly, I wanted to share some example cool healthcare applications. So my talk was not really about healthcare robotics, but since Porto also works a lot in that field, I wanted to share that a lot of these are actually being applied in the healthcare domain as well. So these are just some examples of some European startups that are focused a little bit on healthcare robotics. I particularly really like the medical service one. It's a pretty cute robot, actually. So not all robots look very scary, as you can see. And I think there's a lot of really cool, interesting work in surgical robots as well. The medical service ones are doing a lot of interesting things in terms of hospital delivery or being like some elderly care as well. So there's a lot of interesting things. This is an example also from Johnson & Johnson, where they're training a robot AI model with also Cosmos and synthetic data generation, and then they're training the actual robot stack as well in simulation, which is basically what you see on the right side. And with that, I can finish my talk. Thank you everyone for listening, and if you have any questions, you can join our physical AI community, where you can find more information about robotics, AI, and so on. And then if you have questions, just feel free to catch me at my lunch break. Thank you.